Welcome back. Welcome to the satellite communication course. Today we will learn that eclipse duration. So Earth eclipse, we have seen that Earth eclipse occurs when a satellite falls in the shadow of the Earth. Means we say that Earth, that Sun, Earth. Okay, we have a Sun, then a Earth, and then there will be a satellite. All these devices, all these, uh, all these are come in the same line or a same axis. So in that case, if all these sun, earth, satellite, when all these components came in a one line, in that case, that eclipse occurs. Now we have that sun radiation. Okay, there will be a sun radiation there. We have the earth now, and this portion is nothing but the shadow. And if whatever the satellite is rotating around the earth, okay, so in this particular duration, that eclipse occurs. So what is the total duration of the eclipse? The shadow falls on the satellite. So we need to learn about that. How much is the duration of this particular shadow? So for that, we take an example of a geostationary satellite. Because the geostationary satellite, uh, that rotation of a geostationary satellite, if you see that it is with respect to the Earth, that velocity will or a period is with respect to the Earth rotation. So that's why we consider here the geostationary satellite. If you consider the other stationary satellite, because that rotational period is 90 minutes or 120 minutes, likewise, so they have the short duration of the eclipse occur. But in the case of a geostationary satellite, their plane is on equator itself. So because of that plane is on equator, so there may be a eclipse, that eclipse duration will be a more there. And we consider that geostationary satellite because that geostationary satellite looks like a stationary, and because of that Earth eclipse, so then that satellite is not able to get the supply from the sun radiation, because solar panels are there. So in that case, whichever the device present in the satellite, that storage batteries or whatever the storage components are there, so that is to be used to uh, move the satellite in a particular orbital orbit. So we consider here a geostationary satellite, and for the geostationary satellite, what will be the eclipse duration? Okay, what will be the eclipse duration? So eclipse duration means what? This one is about, we can say, a sun radiation here, and we say that this one is nothing but the Earth, and here we have the, we can say that Earth, and this one is the center of the Earth. Now from this, if you draw, okay, from this, if you draw that, right now we consider that orbit is a circular one. Okay, so don't, it is not a circular one; it is a elliptical orbit. Since it is rotating with a geostationary one, so that's why it looks like a circular one. Okay, so then we consider that from this, okay, this is about your a satellite, that position of a satellite here, and suppose we consider means at this one is about a peak period of that particular eclipse. Okay, so we can consider, and that here we have the, that is about a sun rays here. One is nothing but the sun rays here. We consider, and we consider that this particular portion is nothing but the eclipse occurs. So means the satellite rotating in this given orbit from that point to this point, we say here, we use the word a point here. We supposed to be consider this about A, B. We say this one is about a C. This one is about a D here. Okay, from this, if you consider that this particular duration from B to D, the satellite is rotating, and this belongs to the theta here. And this one is another. Means total duration is about a twice theta we can say. So maximum shadow angle here. Okay, this one is about a shadow angle. We consider that a maximum shadow angle is equal to twice of a theta here, and that theta is to be obtained by consider the triangle. Okay, right angle triangle, and from that we can obtain that value of the theta there. So how we can obtain that value of this particular theta? So we should know that what will be the radius of the earth. This one is about a radius of the earth, and from this to this, that is about a distance of a satellite from the center of the earth. Okay, distance of a satellite from the center of the earth here. Okay, so this one is nothing but a RE. From this to this one is nothing but a RE, and from this to this is nothing but the altitude of a satellite from the surface of the earth. We can consider that R is nothing but what? RE plus H here. So we can calculate that the angle of this particular theta. Okay, so we need to consider here the cosine of that particular angle with respect to the whatever the radius of the earth and this particular distance here. So cos of 90 minus theta. Okay, here the cos of 90 minus theta is equal to RE by, that is a capital R. Okay, I have just mentioned the capital R, and that RE is nothing but what? Earth radius. So we can solve it. 90 minus theta is equal to cos inverse of what? RE by capital R. This one is nothing but a capital R. I am just writing R or a small r. Okay, so this one is a same here. What will be the value of a theta? Theta is nothing but what? We have the 90 minus cos inverse of RE by R here. Cos inverse of RE by R. And our aim is about to consider that maximum shadow angle is about a twice of theta. So this one is becomes a twice of theta. So twice of theta is equal to what? 180 degree minus twice of cos inverse of RE by R. Now we will put the values of this earth radius all in kilometers 6378 here, and we can consider that capital R or small r, that is about a distance from the center of the earth to the satellite here, that we will consider here 42164. And if you put the values here in the kilometers, so that twice of theta, this twice of theta, it becomes what? 17.4 degree. Means we are getting that twice of theta, that is about a maximum shadow angle is about a 17.3 here. But a complete satellite rotates around the earth, means what? It covers the total 360 degree. Okay, geostationary satellite, it rotates around the earth, it takes a 360 degree of a rotation, and that rotation in a period of what? A 24 hours. Means our satellite rotates daily. Okay, daily, that is of a 360 degree. So daily means what? 24 hours duration, and for that 24 hours of a duration, we it covers that 17 point out of that 360 degree, it covers up a 17.4 degree. Okay, that is 17.4 degree, that is about a two maximum shadow angle of a twice of theta. Means out of that 360, it will be, it cover that 17.4. Okay, that is about a shadow angle. So now what will be the time, that time period T? Okay, the time period T, if we calculate here, Okay, we can calculate that time period t is equal to what? Whatever the durations occurred here, and that duration within of what we can say out of that 360 degree, and that will be for the daily of a 24 hours. And if you solve it, we'll get that time period is about 1.16 hour, or we will get that in terms of minute, that is about a 63 minute and a 36 second. That is about a shadow angle, okay, maximum shadow angle, and this one is about your total time period, or we can say that is about a total duration. Okay, that is about a duration of eclipse occurs in that particular period here. That we can consider. So means we can say that from that, that is a maximum shadow angle. Okay, maximum shadow angle. We say it is about a twice of theta. Okay, this one is about a maximum shadow angle, and we say that the total duration, or you can say maximum duration of the eclipse, and that eclipse occurs during the equinox. Okay, during the equinox means all these devices are come in a line. That is called as equinox. So we say here that t is equal to what? A 1.16 hour. That is about a duration of the eclipse. But if you consider the figure earlier we have seen, in that case, we say that, okay, for the earth, and we say this one is about a satellite. So that is about a rotation. Now if supposed to be instead of that earth, we say supposed to be sun, and that sun, around that sun, earth is rotating. This one is about earth. And here we have the satellite now. So now we have seen earlier one particular figure, and in which we have mentioned that the duration of the eclipse occurs. Okay, duration of that eclipse occurs, and that duration of eclipse occurs from, okay, here we can say that is about the duration of the eclipse here, and we have mentioned that it starts from the 10 of October to the 31st of August here, and a maximum peak occur, that is at a 23 September. Similarly, here we have the maximum peak occur at a 21st of March, and it starts from what, 27 Feb to 12 of April. Its eclipse duration, it, there is this one is according to our calendar. So eclipse duration period, here we have sun, earth is rotating here, so around with that the satellite is rotating. So in that case, here we have the earth, and we have a satellite. We have earth, we have satellite, earth, we have satellite, likewise. So that is about a eclipse duration. So at this particular 21st of March and 23rd of September, there will be a maximum duration of eclipse occur. Okay, that is about a maximum duration of eclipse occur. Means at the 21st of March, the duration of eclipse will be what? 1.16 hour, and that will be a maximum shadow angle. Similarly, on a 23rd of September here, that a eclipse duration occur. Okay, that is about the maximum duration occur. So from that we can say that a number of days of eclipse occurs. So this one is the duration. We can say that from 10th October to 31st of October here. Okay, or you can say that 27th Feb to 12th of April here. So in that case, we can find out. Okay, in that case, we can find out. So what will be the maximum duration of eclipse here? So maximum duration of eclipse from this, if you calculate it, so it will be around what? How many days it is? From Feb to 12 April. Okay, from Feb to 12th April. and that will be what? Before equinox. Okay, means what? From 27 to, sorry, from 27 to this one before equinox, and from 21 to 12 April, that is after equinox. Here the equinox. Equinox means what? All these are in a line. Which you can say sun, earth, and satellite here. Okay, that is about the equinox. So we can say that before equinox, that will be what? 22.13 days, and after equinox, again 22.13 days. That is about the duration, that is number of days of eclipse occurs, or you can say that a duration, okay, a duration, that is about the eclipse duration, that is 22 days before equinox and 22 days after equinox. So that is about a number of days here, number of days of eclipse occur. Okay, number of days of eclipse occurs, that is about a 22.13 days. That is what? Before equinox and after equinox. That is about a before and after equinox. So that is about your eclipse duration. Now in this particular period of this equinox duration, in this particular duration, so satellite has to rely on their storage devices. Okay, the batteries or whatever the storage devices are present in the satellite, because they are not getting the radiation from the sun. Solar panels at that time no use. Okay, we could that satellite could not use the solar panels, so that's why they have to rely on the that particular storage devices. Now, because of that, both the devices, that sun, satellite, and earth station. Now here we can say that eclipse means what? A sun, then a earth, and here the satellite. Okay, when both are in line, so in that case, eclipse occur. Now another case is that a sun transit outage. Sun transit outage. In this case, what happened? There is a sun. After that, there is a satellite, and then there is the earth. Means what? Sun, satellite, and earth are in the one line. And then earth station, what happened here in the case? We say that, so here we say that a sun now, okay, this is about a sun radiation. This one is about a sun radiation. And this one is about earth. And satellite is rotating around the earth now. Okay, satellite is rotating around the earth. Now at that particular point, we have a satellite here. Okay, sorry, we can consider that these are the antennas actually. And then these are the solar panels. Now these are the antennas. Now earth is sending the signal to the satellite, and satellite is sending the signal to the earth. Likewise, here we have the sun, and earth is looking for the signal from the satellite. Earth is looking for the signal from the satellite. But at the same time, what happened? Because of that sun radiation, it received the signal from the satellite. Okay, so because of that sun outage, whichever the noise came from that particular satellite, that because of that particular this radiation, okay, that noise will not be received by this earth station. Means generally we consider that We have the satellite, we have the satellite, and that satellite sending the signal to the Earth, or Earth sending the signal to the satellite, the both the way. So while receiving the signal, that satellite Earth station is to be considered that a noise from the sun. But at the time of a sun transit outage, satellite that Earth station will not receive a strong signal from the that particular Earth there, because sorry, from the sun, because of that sun outage. So that is called as a sun transit outage. So in that case, we need to see the whatever the receiver signal, and we need to use the receiver amplifier properly at that particular period of time, so that signal will be received correctly. Okay, that is about a sun outage time. Next, we consider that here we consider that a orbital. Next topic, we consider the orbital perturbation. Okay, orbital perturbation. In a orbital perturbation, perturbation means what? A disturbance. Disturbance goes to whom? Disturbance to the orbit. Means what? A satellite which your orbit is there. Okay, we say that we have the Earth, and then we can consider that this one is nothing but the orbit of a satellite. This one is nothing but the orbit of a satellite. Okay, so now this while rotating the satellite, now we consider always a geostationary satellite. If we consider the geostationary satellite, then there will be a different orbital perturbation. If we consider that low Earth satellite, low Earth orbit or medium Earth orbit satellite, then on this satellite a different disturbances occur. So now what are those disturbances? Because of those disturbances, satellite changes its position, or you can say that deviation in the position, or that position means what? Position of a satellite or deviation in the orbit occurs, and that particular deviation, which is called as a perturbation, that particular deviation is called as a perturbation here. So deviation means what? Whichever the path we have considered, that is from the device, okay, from the satellite to the Earth, we consider right now. This one is about a Earth station is fixed, and this one is about a satellite. Suppose geostationary satellite is a fixed, it is a stationary from this point. But if the disturbances occur, so in that case, we need to change the position of this Earth station, or we need to change the position of the satellite. But what happens if that satellite is a geostationary? So we could not change the position of your station. Our station are fixed. Means likewise you have a dish TV at home. That dish TV is nothing but a earth station. So every year we will not change the position of the dish TV now. So this one is a fix. Now if supposed to be due to the disturbances that satellite position change, so at that particular period of a time, our dish TV is not able to receive the signal, or small variation in the signal strength. So that position of that satellite is to be corrected because of that whatever the perturbation occur. So for the correction, there are the engine present in the satellite, or that satellites are using their storage devices to correct the position of the satellite. Now how that correction is to be done, that we'll see in a second chapter. So consider that what are the causes of the perturbation, why this perturbation occurs. Why the perturbation occur? Because of the non-sphericity of the Earth. Earlier we say that a satellite while rotating in a given orbit, the Earth is not a circular one. Okay. So because of that non, we can say that circular orbit. Okay. There is a difference in the whatever the we can say difference in the path there, altitude. Okay, that is nothing but a non-sphericity. So we'll see that in detail. Okay. Another is about what? Atmospheric drag. Next about the sun and moon's gravity, and then solar radiation pressure. Okay. Now we'll see that first one. In the first, we say that a non-sphericity of the Earth means what? The shape of the Earth is not a circular one. That shape is of a like a apple now. Okay. If you see that a ball, we have the circular in a shape. Okay, ball is in a circular in shape. But the Earth is what it looks like. Likewise, it is not a circle. This one, the shape is here. This will be larger now, but this will be smaller. Okay, that is the water shape, apple shape now. And because of that shape of that Earth is not circular, then there will be a difference in the radius. Difference in the radius. If you see that the Earth radius along with the equator, this one is about the equator. Earth radius along with the equator and the Earth radius along with the north and south pole. This one is the north and this one is the south pole. So generally, if you consider that, if you draw it, so it is rotating likewise. Okay, that is about a rotation of the Earth. Now, if you see the from the north to south, that radius is a difference. There is a difference in the radius. And if you see that on the equator or along with the equator, that radius is different. And there is a difference in a radius, and that difference is about what? 21.4 kilometer. Difference of a what? A radius. Radius difference, what? Radius difference? Because radius along with the equator or along to the whatever the south and north pole. And because of that difference in the radius, that altitude is changes. Okay, altitude of a satellite. If supposed to be these are the orbit, low Earth orbit or a medium Earth orbit, in that case, satellite is rotating around the Earth, and because of that perturbation, okay, that altitude is changes because there is a difference in the radiation in the that on the equator, or we can say along with, or we can say that along with the whatever the north and south poles. Okay, from this north to south poles or from this particular on this particular equator here. And if you consider that if you take a cross section of the earth along with this particular equator, it is not also a circular one. Even if you cut the section of this particular here on the equator here, so even if that particular cross section of that earth is again not a circular, it is an ellipse. Okay, that cross section of a earth is not a circular in fashion. It looks like a ellipse now. It is not a circular cross section of. And because of that particular cross section, so there may be a small perturbations occur for the satellite there. In terms of what? That is about a path. Means path means what? You can say altitude. Okay, that is about a altitude. Or from this from the earth, if you see that value, okay, from this particular earth, so if you see that a longitude and a angle, okay, latitude, in that case there is a small changes in the longitude. Okay, there is a small change, or that change is nothing but a small value. Okay, that change is nothing but the small value, because there is a disturbance in that particular shape of that satellite. And again, another issue is what? So if you consider that, you can say that a satellite is moving from Earth, that toward the east, we say. Okay, so it rotates that toward the east. Earth is rotated toward the east. So satellite is to be rotated toward the east. Okay, satellite is to be rotated toward the east because it's geostationary satellite. So we need a correction in a period of what? For the rotation of the satellite from east to west. Okay, so we need to rotate from the east to west. Means we can say that that rotation of the satellite from the east to west, that is nothing but what? Position of a satellite from the earth. We say it is nothing but a east to west station keeping. That is called as a east to west station keeping. Okay, and if you consider the low earth orbit satellite, or you can say that medium earth orbit satellite, so in that case, that we say earth, and because of that eclipse here, sorry, ellipse here, sorry, not eclipse, sorry, it should be proper ellipse now. Okay, I'll draw ellipse first, and this one is about, sorry, this one is about your earth now, and this one is about your satellite orbit. So this one, so nearest to satellite from the earth, that is about a perigee, and this one is about a apogee, far away from this. So then that perigee and this line of nodes, okay, line of nodes where ascending and descending changes. So this argument of a perigee will change because of that shape of this particular orbit, because of that perturbation changes. So whatever the argument is there from this ascending order to this particular that to the line joining from the center of the earth to the perigee, and that line joining from that that is about whatever the nodes we have, and that ascending point to the line joining this particular perigee point from the center of the earth. That is about the argument. It changes. Okay, that angle changes, and this position of this particular perigee and apogee is again changes. Okay, that distance altitude it changes. So that is because of a non-sphericity of the earth now. Second one, second perturbation is what? Atmospheric drought. This one is about a atmospheric drag. So atmospheric drag means what? So from this earth here, if you see that above this, whichever the altitude we consider, is about a satellite position, this is about a altitude. And in this particular atmospheric region, this is about your atmospheric region. Okay, this is about your atmosphere. So in that case, in this particular atmosphere, there are various atoms present. Okay, means above the earth, there are a lot of atoms present, and that particular atoms have the higher density near the earth. These are what a near density near the Earth. It has the higher density. When you go away from the Earth toward this higher and higher altitude, it's supposed to be Leo to Mu. Okay, you can say that this is supposed to be. We can consider that about a Leo orbit. Then this is considered as the Mu orbit, and this is to be considered as the Geo orbit. From Earth surface to the Leo, there is large density. But if you go away for the mu, so the atmospheric density is the less. If you go away from this, so atoms density, okay. So in that particular atmosphere, so that density will be lower there. Since that orbit is supposed to be Leo, and then because of that atmosphere, okay, because of that density in the atmosphere near the Earth is large, and because of that large density, so what happened? So that because of that large density, that there will be a position changes of the position of the perigea and a apogee. There is a variation in the what we can say that is about a uh, perigea and a apogee. Why? Because of that atmospheric drag, that altitude is changes. Okay, altitude of a satellite changes, and that because of that altitude changes, because that Earth, that Leo Earth orbit is near to the Earth radius, near to the Earth surface, and because of that particular density, so that atmospheric molecules or atoms that changes the position of that particular satellite, and because of that changes in the position of a satellite, so perigea and apogee changes, and that is nothing but a perturbation because of that atmospheric effect. You might have observed that one space shuttle from this Columbia, okay, in which that Kalpana Chawla was present at that time, that shuttle came nearer to the atmosphere. When it came nearer to the atmosphere, because of that pressure, atmospheric pressure in the atmosphere, that shuttle gets heated and it's burnt when it come nearer to the Earth's surface because of that atmospheric pressure. And the same thing happened here. Okay, at that particular incident that Kalpana Chawla died because of that shuttle. Okay, that space shuttle we can say, when it come nearer to the Earth's surface, because of that atmospheric pressure, it burns now. It get heated actually, and because of more and more heating, it get burns. Even you might have seen that nowadays that starship, some spaceship is there only at the time of a coming down. So it okay, it's burned. Okay, because of that atmospheric pressure. So now that atmospheric pressure on this Leo Earth orbit, whichever the satellite, is below that thousands kilometer. Okay, below the 1,000 kilometer of a height. So because of that atmospheric pressure, that altitude it changes, and that is called as a atmospheric drag. Next perturbation, that is about sun and moon's gravity. Now, in the sun and moon gravity, that low Earth orbit satellite and okay medium Earth orbit satellite, these satellites are not affected because they are nearer to the Earth's atmospheric surface. Atmosphere, okay, Earth surface means altitude is low. Here 10,000 to 20,000, and this one is about a 400 to 1,500 something. So these satellites they not get affected. But in the case of a geostationary satellite, that altitude is high. So because of that altitude is high, so there will be effect of the sun and moon's gravity, and that effect only on the geostationary satellite. Okay, because of that gravity, geostationary satellite may get affected. And what changes occur? That is about the inclination. Okay, we can say that orbital, that is the position of the satellite changes means what? Small changes in their inclination. Okay, small changes in the inclination. So we generally consider that here we can say that the what Earth, and you can consider that the what is okay, that is the what orbit of the satellite. So there may be a small inclination. Okay, that is the water position. Okay, there is a small inclination, and that inclination is about what we can say 0.75 degree, or we can say to the 0.95 degree max. Means very small variation means generally what geostationary satellite is to be present on the equatorial plane itself. Okay, this is about equatorial plane. If there is a small changes occur, that is about a 0.75 degree to the 0.95 degree there. Means that is about the annual change in the inclination of the satellite there, position of the satellite. If we are not correcting this inclination every year, so then what happens? So every year there may be a inclination, and because of that 0.75 degree, so next year again, suppose we consider that approximately we consider, for example, we consider that about 1 degree of inclination. So after next year, 2 degree of inclination, then 3 degree of inclination. Okay, likewise. So every day that inclination changes. If that inclination may reach to the 15 degree, okay. So if supposed to be that inclination is to be reached to the 15 degree, so in that case, so what happened? That is about a inclination. So in that case, that station keeping, we say generally a north-south station keeping. So that changes. Okay. So that whatever the satellite and whatever we can say that Earth station keeping point changes, and because of that changes, that there will be changes in the latitude of the satellite there. Changes in the inclination there. Because of the changes in the inclination, there will be a changes in the latitude. And because of the changes in the latitude, the north south station keeping changes. Okay, so you can say that north south station keeping. This point changes. Means it is to be toward the satellite is toward the earth. So this changes, and because of that changes occur. So why this occurs? Because of that gravity of a sun and moon, and that because of that gravity changes in that position of the satellite changes, and north station keeping changes, and because of that particular changes occur, so then satellite is not able to send the signal there. Okay, that is about your sun and moon gravity there. Then another one, okay, another one is about a, and one more is about what? A solar radiation pattern. That is about that you can say. And because of that, whatever the solar radiation, generally, you know that there is a small radiation come from the solar there. And that radiation from this particular solar, from the solar, that radiation pressure on this satellite. Because of that pressure on the satellite, whichever the solar panels are there, okay, that pressure will come on the solar panel. And because of that particular pressure, that position of that satellite it changes. And okay, that orbit of the satellite changes because pressure, more pressure on the solar panel because this satellite has a large, okay, that satellite has a large solar panel, and because of that pressure, that solar radiation pressure on this panel, they may change the orbit of the satellite. That's all about your today's topic of the orbital perturbation. So we have seen that orbital perturbation, and that orbital perturbation causes a four factors. That four factors of what? A non-sphericity of a Earth, atmospheric drag, sun and sun and moon's gravity, and a solar radiation pressure. So that is about our today's